Okay, so in this video we are going to work through the recitation solutions to chapter 11. So paper copies of these solutions are posted up online, but I'm going to work through the video as well. So I have a typical, so I'm going to just basically run through the answers here because I'm assuming that you have already looked at this and you're coming to this for help. If that's not the case, then try to make sure that you are pausing before each problem to give it a try in the first place. Okay, so a typical earthquake produces vertical oscillations, and the frequency of this oscillation is 0.15 hertz. As the earth moves up and down, how much time elapses between the highest point of the motion and the lowest point of the motion? Okay, so we'll use the formula that relates frequency to period for this. So we can say that frequency is 1 over period, or we can say that period is 1 over f. We'll use this version of the formula, so it's 1 over 0.15, and 1 over 0.15 is 6.67 seconds. That's the period. But you would be incorrect to circle C here, because we are looking for the time between the highest point and the lowest point of motion. That is actually only half of a period. A full period would be the highest point of the motion down to the lowest point of the motion, back up to the highest point of the motion again. Right? That would be a full period where we end where we start. Start and end at the same spot. So we are actually only looking, this would be our time axis. We are actually only looking for the time between here and here. So if it's 6.67 seconds from here to here, then this must be half of the period. So we'll divide that by 2 and get that as our answer. For number 2, we have the mass at the end of a string is pulled and released. And we want to see when is the acceleration 0, when is the kinetic energy maximum, and when is the potential energy maximum. So this figure is a little confusing to look at for most people. And actually it's a little fuzzy, so I'm going to try and focus it a little better. Okay. So this is supposed to be sort of 5 snapshots of what the pendulum looks like. So here it is, you let go of it, and it starts to go down that way. And now at point B, it's in its equilibrium position. So it sort of is up high, down low, up high, and now it starts to go back down that way. So if I were to draw this, what we are doing is here's time A, so that one right here, there's B, there's C, and then after C we come back to B, but instead of moving to the right, we're moving to the left. There's D, and then there's E. Okay, so when is the acceleration 0? The acceleration will be 0 when there is no net force on this, okay? So I can kind of look at these snapshots here, and I'm going to go ahead and pick out these 2 things as times when there is no net force. Okay, so here is a time when there is a net force. The 2 forces that are acting on this are the tension force and the force of gravity. Because they don't point in the same direction, they can't exactly cancel each other out. So there is a net force on the sphere right here. And since we know that force is mass times acceleration, whenever there is a net force, there is a net acceleration. Okay, so there is a net force here. Anytime that this pendulum is displaced from its equilibrium position, there will be a net force. So right here, we have that there is a tension force that points up, a gravity force that points down, and these 2 be equal and opposite and cancel. So this is B and D. When is the kinetic energy maximum? Kinetic energy is 1/2 mv squared. So kinetic energy will be maximum when the velocity is maximum. And this ball is, when it's at the top of its motion, it has no speed. And then it speeds up, speeds up, speeds up, speeds up. This is the time when it reaches its maximum speed, and then it slows down, 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 down. No speed, and then it speeds up, 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 up. Fastest, down, 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 no speed, just like that. Okay, so all of right here is when this is all the energy that this pendulum has is all kinetic energy. So this is also B and D. When is the potential energy maximum? Potential energy will be maximum when kinetic energy is minimum. Okay, so we are looking for PE. We can think about this with a couple of different equations. Usually when we think about potential energy, the type of potential energy this ball is going to have is gravitational potential energy. So that was mgh. That's a formula from last semester, so that might not have come naturally to you. But gravitational potential energy depends on the height of the ball. So wherever the height of the ball is the largest, that's where we will have the maximum potential energy. So that would be A, C, and E. A method that might feel more natural if you don't remember this equation from last semester is that kinetic energy plus potential energy remains the same. So energy is constantly sloshing back and forth between kinetic and potential energy for simple harmonic motion like this. So if it is all kinetic energy at B and D, that must mean that there's no potential energy at B and D. So there's no ability to do damage at B and D. Up here, where the velocity is instantaneously zero, that means that there's no kinetic energy in that moment. So it must be all potential energy there. Okay, so for 3, we have a ball oscillating as a simple pendulum. So a simple pendulum just means that we're looking at simple harmonic motion. The period is 2 seconds. And the ball is replaced with another ball that has twice the mass. And what happens to the period? So let's go find the formula for the period of a pendulum. This is my equation sheet. Pendulum is right here. So the formula for the period of a pendulum is this. So let's copy that down. That's the length of the string. And that's gravity, 9.8. So we want to replace the ball with a ball that has twice the mass. There is no m in this equation, so there will be no effect on the period if we change the mass. The only way that we can change the period of an oscillating simple pendulum is by changing the length of the string or bringing our ball to a place where gravity is different, like the moon or Mars. So it started off with t equals 2 seconds. So it ends up with t equals 2 seconds. Next one is I have a ball oscillating as a simple pendulum, so that's more simple harmonic motion. It has a period of 2 seconds. The pendulum is taken to the moon of planet X, where g is half as big. So we'll use the same equation. And now let's say that g gets to be half as big. Okay, so here's period on planet 1, and here is period on planet X. Or I guess this is planet X, and this is planet X's moon. So this is 2 pi square root of L over 0.5 g. It's half as big. So you can make up numbers for this, or you can use letters. I'll do it first using letters, and then I'll step through how we would use numbers on this. So I have a 0.5 in the denominator and underneath the radical that I can pull out of this. So what this is going to be is 1 over the square root of 0.5 times 2 pi square root of L. Oops, L over G, like that. Okay, so I think pulling things out of radicals like this with letters is often kind of hard to think about, but if I was saying that I had the square root of 2 over 2 times 4, that is the same as the square root of 2 over the square root of 2 times the square root of 4. And I encourage you to give it a try, right? So square root of 2 over square root of 2 would cancel, and we'd have 1 over the square root of 4, which is a half. Over here, I would cancel these two, and those would just be 1. So I'd again have 1 over the square root of 4. So whenever anything is a single fraction like this, you can pull all of these radicals apart like that. And this only works if what we have here is multiplication and division. If you added addition and subtraction in here, then it wouldn't work that way. But we're able to just pull the 1 over square root of 0.5 in there. And I think 1 over the square root of 0.5 is 1.4. It's a long number, but if you plug that into your calculator, this is also exactly the same as the square root of 2, but we won't go into too much on how to work around with this. So that's 1.4. So this right here is the period on planet X. So what we've shown is that the period on the moon of planet X is 1.4 times bigger than the period on planet X. On planet X, it was 2 seconds. So we're going to go 2 times 1.4, and we'll get 2.8. If you wanted to do this by making up numbers, you'd be fine to do that, but it'd be a kind of a tricky thing to set up. I think it's easier to do with the letters here because you know that this is 2, so you'd need to solve. So I think you could maybe set the length to be 1 meter or something like that. Actually, we'll set it to be 2 meters just to make sure we don't have any. 1 is sometimes a bad choice. So we'll set this to be 2, and then you'd have to solve for what g is. So you're solving for a number in the square root on the denominator here. And then when you move on to t of mx, you can divide that number by 2. So that would work as well. Okay, so for this next one, I have a wave on a string moving to the right, and at this instant, the motion on a string marked with a dot is doing what? So this right here must be a snapshot graph. Okay, the way that I know that this is a snapshot graph is because it's just, this is, right, this right here isn't time, but this is the y displacement and this is the x displacement. So let's zoom in on this a little bit better. So because this wave is moving to the right, let's draw what this wave looks like just an instant later. So it's moving to the right, so just a short time later, I'll draw dashes here for what that looks like. All right, so a little while later, it's moved this way. But this chunk on the string is right here on the string. It can't move to the right with the wave. So what has to happen as this wave moves through here is this chunk on the string has moved from an initial spot down here up to a final spot up here. Okay, so right at this instant, this chunk on the string is moving up. Okay, so the next problem is I have 2 wave pulses are approaching each other at a speed of 1 meters per second, and how does this look at t equals 3 seconds, given that right here, this is t equals 1 second. So we'll just draw this 1 second at a time. So if it's moving at 1 meters per second, at 1 second, it will be here. At 2 seconds, it will be here. And at 3 seconds, it will be here. So at t equals 3 seconds, 0, 1, 2, 3, 4, 5, 6, 7, 8. And I said that at 3 seconds, this is between 3 and 5. So it'll look like that. This upper wave here, after 1 second, instead of between 6 and 8, it'll be between 5 and 7. There it is at 2 seconds. And there it is at 3 seconds, also between 3 and 5. Okay, so what's going to happen here as these waves overlap is that they're going to superimpose on top of each other. Okay, so we could think about adding these together. So right here at 5 seconds, we'll kind of zoom in between 3, 4, and 5. Right here at 5 seconds, this wave down here is 0, right? It's displaced 0 from equilibrium. And this wave up here is displaced its maximum value. Okay, so we have 0 from the bottom wave meeting with maximum value from here. So we're going to go at 5 seconds. This wave goes straight up. Down here at 4, we're going to have these two waves canceling each other out. Let's just maybe put numbers on this. I'm not just saying maximum and minimum. Let's just say that this is +1 and this is -1, so we can be a little more quantitative about it. So this wave here is +1, and this wave here is -1. So 1 minus 1 cancels, and that will be down here at 0. We come down to 5, and we have this one is at 1, and this one is at 0. So 1 minus 0 is 1, and it looks like that. And now just sort of by filling in these values, we have to kind of connect the dots from 3 to 4 and from 4 to 5. So this is the answer to that problem. Another way that I have seen people draw this that works is to just put these two together. So you can go like this and like that. Okay, and these portions here are where it will cancel, and the portion that's left down here on the bottom is what the wave ends up looking through. So that's another trick to plot those up. Next is I have a set of strings. Each spring has a mass, and each mass is pulled down by an additional 1 centimeter and released so that it oscillates up and down. Which one has the highest frequency? Okay, so what we're saying is that each one of these springs is displaced only 10 centimeters when there is no mass on it. Okay, so if this is right here would be what this spring looked like if it didn't have this mass on it, right? So if it's 15 centimeters from here to here, it's only 10 centimeters from there to there. Same with this one. So this one is 20 centimeters, this one is 12 centimeters, and this one's 15 centimeters. But undisplaced, or without a mass hanging from them, they're all the same displacement. They're not the same stretchiness, right? Obviously, some of them are stretchier than others, right? These two are a good one to compare because they both have 100-gram masses on them. So this 15 centimeters displacement here, this is a stretchier spring than this one is. Okay, so let's get some equations up here. So we're looking for the biggest frequency of spring. So let's write down this formula here for a spring. The frequency of a spring depends on K, which is a property of the spring. It determines how stretchy the spring is, and M. So we'll say F is 1 over 2 pi square root of K over M. Okay. So let's just look for K. So my technique here is going to be, I want to figure out the spring constant of each one of these springs. Okay, so they're not currently being oscillated. What's going to happen is this one is not being oscillated, and we're going to displace it by 1 centimeter, and it's going to oscillate up and down. So let's just find the spring constant of this spring. Using the fact that this 100-gram mass caused it to displace itself 5 centimeters from its equilibrium position. Okay. So this might not be the easiest way to do this problem. I'm going to pull up one other formula. which is this one right here. We'll make it a little bit easier. So the spring constant, or the force on this spring depends on the spring constant and this value here, which is this displacement from equilibrium. Actually, I'll write that on my piece of paper. So we'll have the spring force is negative k times, I'm going to go ahead and write it as a delta x, since we can think about that as being the displacement from equilibrium. Okay, so let's use this formula here to figure out the spring constant of each one of these four springs. Once we know their spring constants, we can use this formula here to figure out the frequency that it will have when it oscillates. I guess in order to figure out this, let's talk about this formula just a little bit. This negative sign here says that the spring force always points in toward the equilibrium position of the spring. We're going to just mostly ignore this. It's something that tells us about the direction of the vector, not the magnitude of the vector. So it's not super important for us right here. Okay, so let's solve this for k. So we'll see that k is the magnitude of the spring force divided by that displacement from equilibrium. So for k of A, that is the spring force divided by its displacement from equilibrium. Its equilibrium position was 10 centimeters and its current displacement is 15. So its displacement from equilibrium is not 15 centimeters, but 5 centimeters. Okay, and now this spring force, we're not quite sure what to think about for this spring force. Well, let's draw a force diagram for this spring. So this spring is sitting here not moving, so it must have no net force acting on it. I know that it has a weight force, because everything always has a weight force. And I know that it has a spring force that points in toward the equilibrium position of the spring, just like that. So this mass here has two forces on it: the spring force that's pulling it up, the weight force that's pulling it down. Since it's not moving, we know that these two must be equal and opposite. So this spring force here, I can think of as being the weight force. We've already kind of taken the absolute value of this, so we've already gotten rid of that negative, so I won't worry about the fact that they point in opposite directions, and I'll just say that this is mg over 0.05. Now I'm ready to plug in that m is 0.1 kilograms, g is 9.8 meters per second squared, and the displacement is 0.05. And plugging in all those numbers, I have 19.6 newtons per meter. Okay, so I am running out of space, so let me pull up another piece of paper. We'll go ahead and plug in do the same thing for B. When you use B, I got 19.6. When I did C, I got I got 49. When I did D, I got 39.2. Okay. So evidently, right, this is a pretty stretchy string. And this is, well, evidently these two springs have the same stretchiness because they have the same spring constant. And that kind of makes sense if you look at it, right? This one had a half as much weight on it, or half as large of a mass on it, and it was displaced half as far as this one here. So it makes sense to think about these two springs as being equally stretchy. So a small k is a stretchy spring. And this big K, this is the stiffest spring. Okay, so now let's return to this formula here. What we are looking for is we want to maximize F. Right? We want to have the biggest F. And in order to have the biggest F, we want to have K be big and M be small. So we need to think about both of these together, right? A big K together with a small M. So our biggest K is here for sure. And actually, we don't necessarily need to calculate any more of this because this one has the biggest K and it also has the smallest M. So we're going to be pretty confident that we're going to win with C. I think when I actually went through and calculated these, I had that FA was 2.2 hertz. So that's 2.2 cycles per second. FB is 1.6 hertz. FC is 3.5 hertz. FD is 2.2 hertz. Okay. So there you go. This one was the largest frequency, so it goes up and down the fastest when it bounces. Okay, and last but not least, a standing wave vibrates as shown. Suppose the string tension is reduced to a quarter of its original value, and what standing wave pattern is produced. So our original standing wave looks like this. I had some formatting issues, but I hope we can still see that. So string tension. So we want to look for a formula that has something to do with the tension force. We're also looking for frequency, and we're looking at standing wave patterns. So this is that we're looking for some sort of like in modes type formula. So when I pull up this, down here in the bottom right-hand corner, I know that the speed of the wave, I think this is the only place where the tension force appears. So the speed of the wave depends on the square root of the tension force divided by the linear mass density. And the mass density here is the total mass of the string divided by the length of the string. So let's put those down so we can have some of the right formulas on here. So we'll say that V is Ft over mu, and mu is M over L. So that sort of checks off that we dealt with the tension. We haven't dealt with this frequency here. We also have no idea what M, L, or V are, so it'd be nice to be able to get rid of them and not have to worry about them. So let's look over here. And I'm going to look over at these equations here. So a string fixed at both ends. That's exactly what this is. And there is the formula for the frequency. The frequency of the nth mode is V over the wavelength. So we'll say that Fn equals V over lambda n, and lambda n, we can kind of keep going here, is n V over 2L. We'll just copy them all down, which is n times F1. So just as a reminder for what all of these things mean, right, this is the n equals 2 mode because it has 2 humps. This is the n equals 1. There's n equals 2. There's n equals 1, 2, 3, 4. There's 1, 2, 3, 4, 5, 6, 7, 8. There. So that's what n stands for here. And so where can we go with this? So we're going to say some things that don't change. We don't know what these are, but we know that they stay the same. Right? This string is going to have the same mass and the same length, right? The length here, that length is fixed, so we're not going to change the length from one to another. So we have the same length here. So this stays the same, and this is going to go down. So we can figure out, this is going to go down as well. We could figure out, well, we will figure out by what factor. So we can figure out what happens to v, the speed of the wave, okay? As the speed of the wave changes, that is going to change. It's going to go down, so let's go ahead and put it down over here. That's going to change v, and that's going to have an effect on f. So let's go figure that out. Again, it needs some more paper. So let's add some more paper here. So let's say that v is f over ft is going to be a quarter of its original value. So this is ft over 4. Let's write this out to be a little bit less confusing. So I'm going to write this to be ft over 4 mu. If you don't believe me, let's just try 3 over 4 times 2. Actually, let's do 4 on top so we can do this math in our head. 4 divided by 4 over 2. The 4's will cancel, and that will be 1 over 2. Take the square root of the whole thing. So that's what this one looks like. This one over here will be 1/4 divided by 2. Oh, be 4/4, excuse me. So this, if we put 4 here, and 2 here, 4 here, 4 here, and a 2 here. Now I have 4 over 4. That equals 1 over 2, the square root as well. So this is an okay way to look at that. And for the reasons that we were talking about earlier, now when I have them set up this way, I can just as easily say that this is 1/4 times the square root of ft over mu. Now I have the square root of 1/4. You can put that in your calculator, or get to where if you see square root of 1 over 4 is the same thing as the square root of 1 over the square root of 4. So square root of 1 is 1, square root of 4 is 4. This is a half. So if this is the final velocity, this is 1/2 of the initial velocity because we lowered it by a factor of 2. So we will say that waves on the looser string okay. All right, so let's go over and talk about this equation now. All right, so this is what we want. Right, we are looking for this in mode. Okay, so let's go ahead and just say that we have Fn is constant. And it equals in V over 2L. Okay, so if I know my before and after speeds, I could set these two things equal to each other. So let's go with in initial V initial over 2L equals in final V final over 2L, like that. So I've sort of set this, using this fact here, I've set these two things equal to each other. And now I can just say, well, I mean, 2L appears on the left-hand side and on the right-hand side. So I can get rid of it. If you don't like just crossing it off from that, we could think about multiplying both sides of the equation times 2L. We do it to both sides of the equation. Now 2L is on the top and on the bottom, on the top and on the bottom. And I can say that in initial, V initial equals in final, V final. So my initial, my V final, we will, actually, so we'll say V final is 1/2 V initial. Or we could say that 2V final equals V initial. Either one of those would be fine. I'm going to go with this one since I don't have a fraction and that's easier. So V initial is 2V final. So instead of writing V initial here, I'm going to write 2V final. In initial was 2. And now I want in final, and that's what V final is. So that became that. V initial became that. In initial became 2. In final, we just transferred over, and V final, we just transferred over. Sorry about that. Let's write this again. So in initial is 2. So we just turned in initial into 2. V initial was 2V final. So instead of writing V initial, I wrote 2V final. In final became in final, and V final just stayed V final. Now I have 2 times 2 times V final equals in final times V final. And since V final appears on both sides of the equation, I can cancel it. So I'll just divide by V final on both sides. And now my V finals cancel. And I can say that 4 is in final. And that's what's left. That might not have been the most efficient way to solve that problem, but it got it done. And there we go. Okay, so I will, good luck going through this and let me know if you have any questions or want to go over anything in a different way.